Okay, good morning. Sorry, I'm running a little behind, and I'm going to try to correct this screen. Give it one more shot here. All right, so last time we left off covering secondary treatment, and we looked at a video. We kind of talked about the general principles of wastewater treatment and kind of the scope of what makes microbes work. We covered some of the terminology, and so today we're going to pick up there, continue talking about, okay, how do we model bacterial growth in a situation where we're growing microbes in order to use them to eat the food. That's going to give us a way to monitor the rate at which the food is being eaten, right? That's the kind of the trade-off there. So that's what we're going to be after here in this session. And next time we'll get into putting it into, so today we'll talk about kind of microbial growth in a system that you just have some microbes growing. Maybe a CSTR where you have some flow going in and out, but no recycle of them. We'll cover recycle, which is what we do in a more practical sense, next time. Okay, so how do we model growth of microbes given that they have the nutrients that they need and want? Well, we can pretty much kind of recognize that anytime we're dealing with, one of these environmental systems, we've got something that's growing or decaying, we can apply our mass balance stuff to it, right? So we're going to do that with microbes, and we're going to do that in such a way that if we're going to grow microbes, previously we talked about them in terms of N, like a number concentration, but for our case where we're growing up a huge amount of them, we're actually going to use X. So X is going to be our microbe concentration, and we're measuring that in milligrams of that volatile suspended solids per liter. This is what we said we can dry up all the solids and then see what burns off, right? So the stuff that burns off and turns into gas is kind of a crude estimation of the amount of bacteria we had. That we basically converted dissolved stuff that would have passed through our solids filter into cells that would get stopped by that filter, and then we burn all that off and say, okay, that's approximately our mass of bacteria. So when we do then some sort of analysis on how X is changing, overall, we're going to say, at least in terms of we're in a growth sense, for a growth equation, we're going to say that's going to be equal to some, typically we would have some rate constant times X to the 1 power. It's going to depend, it's going to be first order with respect to X, because if you have 2 microbes, they can, the amount, it's the doubling time, right? So how many you have will equal, you'll get twice that when they have time to double, right? So it's going to be a first order equation. Now, instead of K here, so this would just be a typical growth equation, right? First order growth, that's pretty simple. But instead of the K, like we've done with some of our other systems like flocculation, we're going to do something that's slightly more complicated and say this is mu. And so this page is kind of showing us where that mu is coming from, right? So actually I'll leave it, I'll say K, and then I'll say mu X. So K then is our rate constant. Okay, so that's to orient us about what we're looking at. So then we have this Monod equation that was developed to tell us something about how the rate at which the microbes are going to grow will depend on how much food they have, essentially. So turns out that if you feed microbes an infinite amount of food, they're just going to have some innate limit. If you feed them only a tiny bit of food, they're not going to reach that innate limit. They're going to be under that. And so that's, as we dissect this equation here, we can see what happens there. So we have mu equals some mu max, so the maximum they could ever grow, the maximum specific growth rate. We can take a look, that's here, right? The specific, maximum specific growth rate. If mu is the specific growth rate coefficient, then mu max, mu m is the maximum specific growth rate coefficient. This will be in per time, so that should give us, we'll notice that's where our per time is going to come from for the overall, because this rate constant has to be per time. So if we look at that equation, we've got mu max times S. S is the bacteria food. That's the substrate that they're going to grow on. We're going to measure that as the BOD, the mass concentration of BOD, milligrams BOD per liter. So with that, when I said an infinite amount of food, we're going to hit some discrete limit. You'll notice we have this mu max times S divided by Ks plus S. This Ks is a constant. We'll come back and talk about that in a moment. It's also in the same units as food, the substrate concentration. So what happens is no matter how big Ks is, if S is infinite, it becomes kind of irrelevant, and then you've got essentially an infinity over infinity. Those will cancel, and you'll be left with just what's left is this mu max. Now, if S goes pretty far down close to 0, then we have a very small number up here times the mu max divided by, this is approximately 0, so you're just dividing that by that Ks. So you can see how at the limits of where we might use this equation, at the high end, we're going to plateau at whatever mu max is, okay? And at the low end, we're just not going to have much growth. It's going to be very slow growth. Okay, so that's kind of practically speaking, that's what that model does, and as we'll see in a minute, we can plot the actual growth rate coefficient, the mu, versus substrate concentration, and we'll see just that. We'll see some sort of a relationship where it's getting faster and faster, but it plateaus. Okay, so then the last thing to explain here is this Ks is, and I have this twice. Delete one of those. The Ks is called a half velocity constant, milligrams BOD per liter. This is defined as, and we'll see this graphically in a moment, the amount of food where the bacteria are happy to grow, like they're halfway happy, right? They're halfway to their maximum. So this is just a little bit arbitrary, but again, looking at the equation, it's, if we say that, we can kind of get a feel for it, like if they have as much food as they'd like to have their maximum, then Ks, or then S is large compared to Ks, but Ks itself is kind of the halfway point there. All right, so let's just take a look at that. So if we have a graph where we're plotting our growth rate coefficient, our rate constant for this equation, we'll have some mu max up here. That'll be the maximum we'll ever reach, and we have substrate as the x-axis. So when we have no substrate, we're not going to have any growth. If S is 0, mu is 0, right? So then as soon as we add some substrate, we'll start having some growth, and what it will ultimately look like is something like this, right? And it'll eventually reach our mu max. So then to find Ks, this is not something we're actually going to do in a problem. I'm just kind of showing you where this is coming from and why it fits into the equation. If Ks we define as the halfway point to mu max, the amount of food where we've reached that halfway point. Really, this is, I shouldn't put Ks there, I should put mu 1/2 mu max. That's the amount there. So we can find Ks then if we bring this over and say, all right, at this point, we've reached the halfway mark in terms of the growth rate coefficient, and then this mark is our Ks. This is in milligrams BOD per liter. Okay, so that's kind of where this equation is coming from. Typically, you'll be given some rate or some constant for Ks. That's going to generally vary based on the microbe, right? How much food do they take before they're happy? How much, how does this play out in practice? Maybe some microbes are happy to just have a little bit of food. And in fact, if you get into some of the more advanced biotechnology, culturing kind of stuff, there are some microbes that do well with some sort of a pattern of feast and famine. So some microbes will outcompete everything else if there's just plenty of food, and some microbes are better equipped to withstand periods of starvation. So if you, when we go and try to culture microbes as a way to grow them and to study them or do whatever, not all microbes are culturable in the standard sense. So sometimes they'll have to have more variation in order to outcompete other stuff. So those are harder to study. I've just heard some interesting talks over the years about that kind of intermittent culturing can be important for some microbes. But in general, for the wastewater, we're generally just giving them food the whole time, for the most part. So we're looking at what's going on. But this does help us understand if the amount or type of food had changed suddenly in our influent, that could disrupt our microbes. Maybe something else, some other type of microbe starts growing, and that could actually become a big problem if something starts growing that causes a lot of floating material instead of stuff that will settle. Everything bulks and floats and passes through our clarifier without being separated, and we have a big problem. All right, so there's a good reason to concern ourselves with this type of dynamic. Okay, so if we put this in a bottle and watch what happens, it turns out there's more than just growth that's important. We are also going to have death of microbes, and we're also going to have the consumption of substrate. So we're going to have growth, of course, dx dt as a growth, that's mu x. We're also going to have some value, so this is, we'll just say that's growth. But then we also have some ds dt, the change of substrate over time that we might be interested in, and some sort of a decay equation, which we'll come back to, but that would also be dx dt equals negative something, right? Probably a first order with respect to x. So when we put those things together, those different rates that are going to happen in a jar with some discrete amount of substrate, what's going to happen is we'll have over time, usually it takes the microbes a little bit of time to warm up to the fact that, oh, we've got food, we're happy, we can grow, let's start reproducing. Let's start eating this and reproducing. So there's usually a few hours of a lag phase where nothing too much happens. Sometimes this might be 3 to 4 hours. By the way, if you're ever concerned about food safety at some sort of a church picnic or something like that, and you've got something with perhaps raw eggs in it or something to that effect that should be kept refrigerated, and it's just sitting out in the warm sun and all day long, and then you eat some in the evening and food poisoning. Well, one way to avoid that would be to eat it while it's fresh before this lag phase is passed. Because the risk is that you have microbes that maybe it was fine to eat it when you started the picnic, but after it's been sitting out for 6 hours in a nice warm environment with delicious, microbe food there, well, microbes will be growing, right? So if there's something bad growing there, then that's when you end up with an issue. So eat that potato salad or whatever it might be early while it's cold, and not later in the day. Because this is what we're dealing with. Is as soon as they kind of wake up and recognize they have a good environment, they're going to start doubling, and this will happen pretty quick. So if this is kind of that 3 to 4 hour mark, somewhere around here, I don't know, maybe it could even be, I'm going to say 2 to 4, might not take that long. Then they'll start doubling. So if it's been 6 or 8 hours, you suddenly have 10 or 100 times as many bacteria as you had a few hours ago. So because this is the log scale here, and so it might look something like, here, different log increases here, right? It might look something like that. So then for a while they will grow, and in a typical media broth thing with, let's say, E. coli, something that grows pretty quick, then they're going to consume most of the food possible, and they'll have done a lot of this, they've gone through this growth phase, something like overnight, something like 18 hours. If you ever work with a petri dish and you're counting, like doing the colony counting stuff, you'll get a visible colony if you leave the thing overnight with something like E. coli. So at some point, they've used up as much nutrients as is easily accessible nearby. And from there, you'll have kind of slower growth. And in a jar type of situation, you'll probably have a situation where you end up having a matching death rate and growth rate. There's still a little bit of food, and they'll certainly cannibalize each other's dead bodies for munchies. That's just sounded awful. But there will be kind of a steady state at some point between the death and the growth. So that would be a stationary phase. And ultimately, they run out of food altogether, practically. There's probably still a little bit of growth, but overall the decay is way outpacing any remaining growth. So this would be, death would be greater than growth. So of course we could also recognize that over here this growth would be higher. And if you think about this on a petri dish, well, it's a bit of a different story. Your little colonies that are growing will ultimately get bigger and bigger and bigger over time because the microbes find more food and can keep going, but that's a pretty slow process. So unless you left them in the incubator on accident for like a week, if you do that, you'll see they're like slowly spreading across the whole thing. But over one day, you'll see they kind of have a bit of a physical limit, and after that, it's really pretty slow because they have to encounter new media to grow from. So that's kind of a picture of how the growth kinetics happen in sort of a batch system. And an important part of this is if we were to plot the substrate concentration in all of this, we could say, if we had another axis here, milligrams BOD per liter, this would look something like this. Right? It would kind of do the inverse of what's there, of the growth of the microbes. So we'll talk more about that in a moment, but the point there is that we could observe over time, if we measured it, the amount of substrate there, and also the amount of bacteria. And monitoring those, we would see the bacteria growing, the substrate decreasing, and we can make some relationship between those to understand what's happening with our S, which is ultimately what we want to treat with a wastewater, right? That's ultimately what we're trying to remove. We can monitor that and understand something about it based on what's happening with X. So that's kind of where we're going with it. Okay, so the growth rate. We have that as dx dt is mu x. We could expand that to say that's x times what we have with that Monod equation, right? The mu max s divided by ks plus s. And in order to relate that with how much food we're using, we can describe what we would call a yield coefficient. And this is going to let us get to a substrate utilization rate. So the amount of substrate we're using will depend on how much bacteria we have growing and how much mass of bacteria we get per mass of food that is consumed. So this substrate utilization rate, that will we can get there using this yield coefficient y. We have an equation for the maximum specific substrate utilization rate that can help us with that. Sounds very similar to mu max, right? So K should be related to mu max. So we have a couple new variables here, and just a quick side note, I'm going to follow the book's nomenclature. There are lots of different Ks, so be warned that we have a lowercase k here. This is describing the maximum specific substrate utilization rate coefficient. We have this uppercase K with Ks. This is not the same thing, right? We've got the little X marks there, so recognize that's different and set that aside. And then we'll have a KD in a minute for coefficient for death. So we'll have potential for confusion. These will all be on your formula sheet, so just make sure you understand which one's going where with all of that. Okay, so this maximum specific substrate utilization rate coefficient will have units of milligrams BOD, so milligrams of the substrate we're using, per milligrams VSS, so that's the mass of bacteria per time. So if we divide that, if we can find that by taking that maximum specific growth rate, mu max, which is per time, and divide it by that yield coefficient, which is in amount of mass of bacteria we get per mass of substrate we use. So all of this is like trying to say it all out loud feels like I'm muddling the waters just trying to say it. So take a step back and recognize what we're yielding. When we want to yield, we're getting mass of bacteria per food. That will probably help stick it in your mind a little better. Then when we have a substrate utilization rate coefficient, this one should include time because it's a coefficient kind of thing, and we're using substrate, so this will be mass of substrate per bacteria. Per mass of bacteria. Per time. So trying to say it all out, and I don't know, the way I have it written here doesn't feel super intuitive on the slides themselves, but think about it in that manner, right? Yield, the mass of the bacteria per food. Utilization, mass of food per bacteria over time. Okay, so hopefully that can make it clear and help you kind of just streamline that understanding. So what that does for us then is that lets us get a rate of substrate utilization. That's this RSU here. And we can relate that inversely or negatively to the growth rate. So if we're growing fast, then we are using substrate fast, right? So, but substrate goes in the opposite direction. We're consuming it, whereas we're growing, we're producing the microbes. So our SU is going to be equal to negative R of G, and it's just going to be divided by this yield coefficient. So we could do that in reverse too. We could solve for R of G in terms of RSU. Typically, we'll be more interested in how fast are we using our substrate. Okay, so if R of G is mu x, then we could say, you know, a follow-up from this, we could say RSU is going to be negative mu x over y. All right, so then the only thing left for us to get a handle on is RD. What is the rate at which the microbes are dying? And this is generally going to be quite given. It's just going to be some standard constant, right? We have a known amount of microbes dying over time. So we'll have another rate constant KD. So our RD will be negative KDX, right? It'll be first order. The KD will be a death and decay rate constant per time units, accounting for the death there. So that'll give us a way to get some net growth rate. We can call that R prime of G. So the net rate at which we've got bacteria growing will get us the net change in X. And that's going to be the growth rate plus the decay rate. That's the R prime of G is 0 at our stationary phase, right? R prime. It's positive during the growth phase, and it's negative during the decay phase. We kind of already wrote that up as a description. Okay, so then we can rearrange these things if we'd like to and get this net growth rate in terms of substrate utilization and that death rate. So that might be helpful sometimes. In general, recognizing that sometimes we'll need to know the amount of bacteria to find the substrate can be useful, and vice versa. So there's a few dynamics there. All right, does that make sense? Good on that? Okay, so we're gonna set up a problem here in a moment. We'll use some default parameters for some of these values. I will write these up for you in a moment. But these default parameters here, this is a table in our book. It gives us typical ranges for the different values here. So we see our utilization rate coefficient, K, lowercase k, our maximum specific growth rate coefficient, mu max, that half velocity constant Ks, the yield coefficient, and the death decay rate, Kd. So each of those have a typical range we could take a look at, and then some default value for if we wanted to solve some problem, we didn't know what to start with. This is a pretty typical one. So we're going to use those default values here for example 6.9 from our book, where we have BOD consumption in a pond. So it says the shallow pond depicted here stays well mixed due to wind and the steady flow of a small creek. So we've got a situation where we say this is pretty well mixed, good enough for a CSTR, right? And we have flow through, meaning it's not batch, right? So we've got flow and it's well mixed. So we're going to have a CSTR type system. We'll take a look at the rest of the problem prompt in a moment, but I'm just going to highlight what we are looking for is kind of given in the caption here. The X final and the S final are question marks. So what we want to know, what we have on the left is Q, X naught, and S naught. We have some amount of X and S in the pond. It is well mixed, and we have our growth and our decay rates in there, and a substrate utilization rate accordingly. And what we want to find is how much X is going out and how much S is going out. And since this is a CSTR, we can remember that XF is equal to just X, and SF is just equal to S, right? They're using F here just to say final. I think in the past, maybe we said, we could say effluent or something like that. Okay, so that's what they're after. So I'm going to give you some time. We'll start this problem a little bit. I'll give you some pointers, and then give you a couple minutes to think about kind of how to approach the problem if you were to begin it, and to get your gears turning towards that. Okay, so if the microbes in the pond consume the inflowing biodegradable organic matter according to typical kinetics, determine A, the BOD leaving the pond, that's the SF, right? B, the BOD, or the biodegradable organic matter removal efficiency of the pond. So removal efficiency, we can think to ourselves, well, we don't have some specific efficiency term here. This is not water efficiency or anything like that. So removal efficiency, we could call that what we start with minus what we ended with divided by what we started with times 100%. Right, so we'll just use our answer to part A to get that, that value. And then C says the concentration of volatile suspended solids leaving the pond. So that's going to be our XF. Okay, and I included the beginning of the solution here to kind of get us a little bit primed. So it says the pond can be modeled by us as a steady state CSTR because it's well mixed, and we'll assume the stream flow has been at a steady flow rate and composition for a long period. So basically the S naught, that S coming in, if that's constant for a long time and the flow rate's not really changing, then we probably could reach a steady state. That's kind of what they're saying. All right, so then A says first set up a mass balance on the microbial mass using the pond as a control volume. And the variables in this, in this figure, and we can start that by saying 0 is equal to Q times X naught minus Q times X final plus V, so in that volume, the R prime of G, so the net growth rate. Now what you'll notice here is we're solving for S, and immediately the book's like, okay, let's do this by making a mass balance on X. So it might be a little counterintuitive there. You might think to yourself, well, why aren't we doing a mass balance on S? We need to solve for S. So this is counterintuitive. You'll see as we work through this that it ultimately makes sense. And again, that relationship between knowing X gives us S and knowing something about S can give us info on S, or knowing something about S gives us information on X. We kind of cross paths here, and it ends up working out. So start there and see how you can do. I'm going to take a moment to transcribe some of those default values, but you can start on your mass balance certainly without those particulars yet. So take your time, feel free to work together, and or ask questions. I'm going to try to write down several of the equations we just covered for you as well. All right, so for part A, I'll kind of step through it with you a bit here, and we can solve that, and then I'll give you a couple minutes to work on part C once we clear A and B. So setting up our mass balance, we've got 0 is equal to what's coming in, qx naught, minus what's going out, qx, plus this growth rate of x, but it's the r prime, right, the net growth rate. So it'll be v times the r prime of g. And that part was all given. What we'll recognize is x naught is 0. So if we take a look up here, we see x naught is 0. So that term goes to 0. And so we're left with 0 equals 0 minus qx plus v times this growth, which is x mu max s times ks divided by ks plus s, subtracted by the death, which is v k dx. Right, so all that in the volume is where the v's are coming from. And if you notice, we can simplify really well if we divide by x and if we divide by q. So here's the really neat thing, that because we have no x naught, that x naught term drops out, and then we have 3 terms all with x in it, and we can divide everything by x without getting in trouble with a 1 over x somewhere, right? It just all disappears. So the x's cancel out of this system because we have no recycle, because we have no influent coming in. So our derivation here, you'll notice, is very specific to a no recycle case where we don't have a meaningful amount of bacteria coming in. There are enough to get the thing started. You know, there's some bacteria kind of living everywhere, but not like some significant mass of it. So given that, the following solution is valid for the pond type of example where we are not recycling. Next time we're going to go into the recycle and sort through how we deal with those systems. But for the moment, we're going to continue with this mass balance and take a look. So it turns out we can get rid of all x terms. That's really handy because we have 2 unknowns, right? The x and the s. Normally when we solve a mass balance, we're just trying to deal with one unknown, and we're just dealing with that only. So in this particular case, that becomes very convenient. Dividing by q also gives us theta instead of v, and just gets rid of a q here. So we end up with -1 plus theta mu max s divided by ks plus s minus theta kd. And from here, it's a matter of algebra to solve for s. So I'm going to work on that for a couple minutes here. We just have to expand something out, and I have the formal answer to double check, but basically we're going to separate, going to get the s terms by themselves so we can handle them. All right, so I'm going to go ahead and get a couple things on the left side. So we'll say 1 plus theta kd is equal to mu max s, and we'll go ahead and multiply both sides by ks plus s. So we'll end up with ks plus s times 1 plus theta kd equals mu max s on the right. Okay, so I basically just need to expand this out on the left. So we'll go ahead and say ks plus ks theta kd plus s theta kd. All that's equal to mu max s. All right, so then I'm going to subtract mu max s from both sides and subtract this ks plus ks stuff from both sides, kind of getting all the s terms by themselves here. So we'll say s plus s theta kd plus mu max s equals Ks plus Ks theta Kd. So I'll factor out the S here, say this is 1 plus theta Kd plus mu max equals, I'll go ahead and factor out the Ks here, Ks times 1 plus theta Kd. And then we can get our final equation here for S. I'm just going to put it here to say this is going to be Ks times 1 plus theta Kd, if I've done all this right, divided by 1 plus theta Kd plus mu max. We can check the units first of all to see if we are in the right order. So S should be a substrate, right? That's milligrams BOD per liter. Ks is the same, so that our units should be satisfied so long as everything else cancels with the Ks up on top there. So in the parentheses here, we have 1 plus theta times Kd. Theta is time, and Kd should be per time. So assuming that when we solve the problem, we put those in the same units, per day or something, should be all right. On the denominator, we have 1 plus theta Kd, again, that same deal, and mu max on the bottom. So I think I thought I had something missing here, so if you see that, let me know. It should be, yeah, it should be theta times mu max, right? That would allow it to cancel. So where did I leave off at theta? Because I think there should be a theta here. Right here. Okay. So we're going to fix that real quick, and then we should be good. I did feel like something was wrong, so I'm glad we caught that. Okay, good. So again, this is very specific to the case where we're doing essentially a pond or some CSTR with no meaningful bacteria input. This equation, we can derive it, and I think I'm giving this to you on the equation sheet, but remember that this is very specific to a no recycle case with a CSTR with no meaningful concentration of bacteria input, right? And this is the mass balance to solve for S by taking the mass balance of X. So it's pretty neat that that works out. For this particular problem, we can find the theta, put in these terms, and finish out the solution here. So I'm just going to give a little note. This is CSTR, no recycle, X naught equals 0. Okay. If we put in the terms, need to solve given the 50 cubic meters per day, the 200, well, we can solve that by hand actually. So theta is V over Q. That's 200 over 50. 200 cubic meters divided by 50 cubic meters per day. So this should be 4 days. So with that, then we have everything we need, and it turns out that they just made the answer equal to the problem number, example 6.9. Milligrams BOD per liter. Okay, so that's the answer to part A. Make enough sense with that? Okay, part B then, we'll quickly go through. That's going to be, what we start with is 95. What we end with is 6.9 divided by 95. And anybody have that? I think I probably have it. 92. Okay. It's 92 point what? Okay. All right. Great. How far did you get on A? Did you finish A? And did you get it or get pretty close or?
I did it differently, but I got it somehow.
Okay. Did you end up with kind of a same equation for S, just took a different route?
Yeah, it was a little different, I think.
Uh-huh.
But like I had subtraction at the bottom instead of addition. But
Interesting.
it still was 6.9. I used
Okay.
I don't know, I used a bunch of stuff.
Okay. Well, good. Okay, so then part C, did you guys start on that yet, or? Okay, yeah.
On part A, that last step, I think we didn't subtract the other side.
Oh, so
I think you just moved it
when I
out of the line underneath.
right here to here should have been a subtraction, right?
Yes.
That makes sense to me. That would make sense about that. So this would be a subtraction. Is that the difference that you had, or is there more than that? You see my priors.
Yeah, that wasn't it.
Okay, in my notes I have both of them as subtraction, and I just missed it. So would it, let's see. Is this one also supposed to be a negative here? I missed something way earlier. Check this real quick. I think I did do something wrong. One thing you could do is you could subtract these two from both sides. So you'll end up with mu max S times theta minus S minus this. So what I did instead was I was supposed to subtract this from both sides. So this would be a negative. I just moved this to the other side. Hang on. What I should have done, I'm going to rewrite this, just this part. I think I see what I did. I swapped sides for convenience to put this on the other side, but the way I did it, I should have been subtracting everything and then handling it appropriately. So if I'm going to move this to the other side, just to put it over here like I did, what we should end up with is mu max S times theta minus S times theta KD. So then when we get this piece, I'm just going to rewrite from here. This will simplify to mu max S minus 1 minus theta KD, which is actually the solution I had on here. So good catch there. You did it right, and this morning I got it wrong. So then this becomes mu max. Sorry, that should have been a theta. Mu max theta minus 1 minus theta kd. Look better? Okay. Good. Sorry about that. Okay, so part C, this time we're going to approach it as a mass balance. Since we did a mass balance on X already, this time we're going to do mass balance on S. And essentially we're going to use the same bunch of parameters that we had here. And I'm just going to screenshot that for us and add it in. So pardon me just a moment. All right, there we go. Okay, so take a couple minutes to do that, and I'll join you, and we'll finish that out in a moment. Oops, sorry. Okay. All right, so I'm gonna finish out here with you real quick. So we've got this mass balance on S, 0 equals QS naught minus QS plus V, our substrate utilization rate. So that's the key, is to add in the substrate utilization rate, and we can get that from the growth rate, and that's where X comes into play. So our substrate utilization rate is basically the negative growth rate divided by Y. And if you're following as I did things, I forgot the Y for a moment, but we just put that in here, just like any other mass balance, and we can divide by Q to simplify. That'll help. So we've just inserted these things in here. We divide by Q, we get S naught minus S. So 0 equals S naught minus S minus theta X times all this stuff. Now what you'll notice here is we can actually swap in K here, because K is equal to mu max divided by Y, so there will be a K on top here. So as we simplify, we'll notice, so we're going to solve for S, but what we'll notice here, stop that, is, so we can say 0 is equal to S naught minus S minus theta K, excuse me, theta X times this K will come to the top. It'll be K times S divided by KS plus S. So now we just solve for X, and we can do that. I'm going to go ahead and add this entire piece to the left side, so it'll be theta X KS divided by, that's a lowercase k times S, right? Divided by this lowercase s, the half velocity constant, plus S equals S naught minus S. So when we solve for X, at the end of the day, it becomes S naught minus S times KS plus S, all that divided by theta XK. If PowerPoint will let me. It's not going to let me, so. Okay, so with that, we should have all the pieces. And if I look back at my notes, X should be 43 milligrams ESS per liter. Let me double check that I got the equation right. Bless you. Yeah. Okay, does that make sense? All right. So there we have it. Got the growth, the depth, and the substrate utilization. All right, so we'll end there, and we'll see you on Tuesday. I think I posted some Moodle quizzes. I'll double check, but just some kind of activities, so please participate in those, just kind of as a little knowledge check kind of a situation. All right, so have a good weekend.